If you look at a modern aircraft or a steel bridge, you see a triumph of rigidity. Our engineering history is largely a story of making things stiff enough to withstand the elements. We use heavy beams and thick plates to resist force, but nature takes a different approach. A bird's wing isn't a collection of rigid parts held together by hinges. It is a fluid, adaptive system. For billions of years, evolution has been perfecting structures that prioritize flexibility over brute strength. We are now entering an era where our machines are starting to look less like boxes and more like organisms. The idea of looking to nature for engineering solutions isn't new. In the late 15th century, Leonardo da Vinci filled his notebooks with detailed anatomical drawings of birds and bats. He realized that flight wasn't just about flapping, it was about the shape of the surface and how it interacts with the air. Da Vinci's sketches of ornithopters attempted to mimic the musculoskeletal system of a bird. While he lacked the materials to make these machines fly, he established a core principle of bionics, that nature has already solved most of our structural problems through millions of years of trial and error. Consider the owl, a predator that relies on silence. Most birds create a distinct whooshing sound when they fly because of the air turbulence rolling off the trailing edge of their wings. Owls have evolved a unique solution. The primary feathers on their wings have a serrated, comb-like edge. This fringe breaks up the large, noisy air vortices into smaller, silent microturbulences. By studying this specific geometry, engineers are now designing ultra-quiet cooling fans for computers and even serrated trailing edges for wind turbine blades, significantly reducing noise pollution in rural areas without sacrificing energy efficiency. In traditional aviation, we control a plane using flaps and ailerons, discrete panels that move up and down on hinges. This creates gaps and sharp angles that increase drag. However, new research into morphing wings is changing this. Using flexible composite materials and internal actuators, engineers can now create wings that change their entire shape continuously, much like a living bird. These wings can curve and twist to optimize lift at different speeds. By eliminating the gaps between flaps, we reduce fuel consumption and allow for a much smoother, more efficient interaction with the atmosphere. Bionics isn't limited to things that move. It's also transforming how we build stationary structures like bridges and skyscrapers. To understand this, we have to look inside ourselves. Human bone is a marvel of structural engineering. It isn't a solid, uniform mass. If you look at a cross-section of a femur, you'll see a dense outer shell and a porous internal network called trabecular bone. This lattice is organized along the lines of maximum stress. It provides incredible strength while remaining lightweight. By mimicking this internal lattice, engineers can create 3D printed metal beams that use 40% less material while supporting the same load. This bone-inspired geometry is now being applied to large-scale architecture. Imagine a bridge where the thickness of the steel isn't uniform, but instead varies based on exactly where the weight of the cars is distributed. Using generative design software, computers can grow bridge supports that look almost organic, with branch-like structures that mimic trees or skeletal systems. These designs look strange to our eyes because they don't use straight lines or right angles, but they represent a more efficient distribution of force. In these structures, form truly follows function, just as it does in a forest. The secret to nature's success often lies in its materials. Human engineering typically uses homogeneous materials. We make a whole beam out of one type of steel. Nature, however, uses composites. A tree trunk is a sophisticated arrangement of cellulose fibers embedded in a lignin matrix. This allows the tree to be stiff enough to stand tall, yet flexible enough to bend in a storm without snapping. We are now developing functionally graded materials that mimic this. We can create a single piece of material that is hard on one end and soft on the other, allowing for components that absorb impact without breaking. One of the most difficult challenges in engineering is fatigue, the tiny cracks that form in metal over time and eventually lead to failure. Living organisms handle this through self-healing. While we haven't yet built a bridge that can heal a crack the way a bone mends a fracture, we are getting closer. Scientists are developing concrete infused with dormant bacteria. When a crack forms and water enters, the bacteria wake up and produce limestone, effectively scabbing over the wound. This shift from passive structures to active, responsive systems is the ultimate goal of bionic engineering. As we look toward the future, the line between the mechanical and the biological continues to blur. We are moving away from the idea of dumb materials that simply resist force until they fail. Instead, we are building structures that sense their environment and adapt. A bridge might stiffen its own supports during an earthquake, or a skyscraper might shift its center of mass to counteract the wind. By observing how a blade of grass survives a gale or how a bird glides on a thermal, we are finding more elegant ways to exist within the laws of physics. The 3.8 billion years of evolution behind us represent the most rigorous research and development phase in history. Every animal and plant we see today is a successful solution to a problem of survival. By shifting our perspective from conquering nature to learning from it, we are discovering that the most advanced technology isn't necessarily the one that is the most rigid. Often, the strongest and most efficient way to build the future is to look at the elegant, flexible, and resilient designs that have been right in front of us all along.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.